Okay, now I want to dig into the question of, have we peaked? Have we reached the best sorting algorithm that we possibly could? So one of the things you notice about merge sort, quick sort, insertion sort, and bubble sort, and all the sorts we've gone over so far, is the steps that lead to swaps and reordering things occur when we answer a question about the order of two elements. So when I do a comparison between two elements, that's the only time I would ever swap something. Okay? That's true out of all the algorithms we looked at so far. So you can see it here in quicksort when I'm doing this comparison. You can see it here in merge sort when I'm merging things together. That's the only time things get shuffled around. So let's consider all such algorithms where what we're allowed to do is answer a yes or no question about just a pair of elements. And we call these comparison-based sorting algorithms. So what a sorting algorithm is really doing is it's telling us what permutation of our list do we have, as I started off talking about. I mean, you can check all possible permutations, but it's probably better if you narrow it down in a smarter way. So let's try to think about how can we narrow down the possible permutations by just comparing two elements at a time. Okay. So without loss of generality, I'll consider an array that has the elements 1 through 4 of length 4. And there are 4 factorial, which is 4 times 3 times 2 times 1, which is 24 possible permutations of a list of length 4. All right. And I want to answer yes or no questions about the arrays. And based on those questions, just comparing two elements at a time. Based on those questions, I want to try to narrow down the possible permutations. So let me just throw some questions out there and we'll see what happens. So we'll say, is x at index 0 less than x at index 3? So is the first element less than the last element in the permutation that I happen to have? So based on the answer to this question, I will branch out in one of two directions. So it's either true. So it's true and I go to the right, or it's false and I go to the left. So let me try to break these down to those cases. Okay. So x0 is less than x3. That's certainly true for all of these. It's true for this one, this one, this one, this one. No, not for that one. Okay. So let me just try to get all the yeses first. These are all less, but that one's not. This one is. This one is not. This one is. This one is not. Okay, so this one is. That one's not. This one is. 3 is less than 4, but 3 is not less than 1. 3 is not less than 2. 3 is not less than 1. 4 is not less than 3. 4 is not less than 2. 4 is not. So, okay, so all these we know are going to be over here. Okay, cool. All right, so I've managed to. Let me try to keep these roughly together. Oops, what happened to that? Okay. All right, so if I answer this one question, looks like I'm able to kind of divide my possibilities roughly in half. Okay. So let's try to think about, well, what other questions could I ask once I've branched off? So, all right, so I've already said something about comparing the first element to the last element. What if over here I compare the first element to the second to last element? So let me say, is x0 less than x2? So I can ask that question over here if I go down this branch. So it's either going to be yes or no. So if it's a no, let's do that. So, okay, is 2 less than 4? Yes. Is 2 less than 3? Yes. Okay, so these are going to go into the yes category. Is 3 less than 4? Yes. Is 3 less than 4? Yes. Is 3 less than 1? No. Is 3 less than 2? No. Is 4 less than 2? No. Is 4 less than 3? No. None of these are going to make it. Okay. No, hang on, sorry. I need to say is, okay, 3 is less than 4, 3 is less than 4. Now I have 4 is not less than 2, 4 is not less than 3. Right, yeah, none of these are going to make it either because they all start with 4. Okay. So that time I didn't cut it quite as evenly, but I was still able to narrow down the possibilities. Okay. So that's a yes and a no. And of course I could ask the same question on the other branch over here. And let's try to answer that question over here and put them into the appropriate places. So here, I've also got my yes or my no. Okay, so here, 1 is less than 3. Yeah, here they're all going to pass. 2 is less than 3. 2 is less than 4. 2 is not less than 1. 3 is not less than 2. 3 is not less than 1. Okay. So maybe this wasn't as good of a question. It didn't split us as evenly. Okay. But these are the sorts of questions you can ask. So if I've asked 2 questions, I've been able to narrow it down this much. And I can keep asking questions, and eventually I'll be able to narrow it down to a single possibility. So the thing we need to think about is how many questions, or what is this fewest number, if I'm really smart, what is the fewest number of questions that I can ask in order to uniquely identify which permutation I have? So let's think about that. So we have to cut down a possibility of n factorial. So there are n factorial possible permutations. The best we can possibly do by answering a yes or no question is to cut the possibilities in half. We seem to do a pretty good job of that on the first round. I didn't seem to do as good of a job on that at the second round, but maybe I just didn't ask the right question. Okay. In this particular example. Okay. But the best I can possibly do is, when I do a single comparison, is to have the number of possible permutations. Okay. So, all right, so then the question is, ideally then, if this happens every time, how many questions do I need to ask to get to a single possibility? Well, so that's like asking how many times, so in other words, how many times do I need to have n factorial in order to get to 1? Well, this is simply the log base 2 of n factorial, right? And we've already done this, right? Log base 2 of n factorial, we did this when we were thinking about all the permutations, the brute force. So that's why I actually just copied this in here. So now we're thinking about lower bound on comparison-based sorting. So while the log base 2 of n squared, we can use the rules of logarithms to split that up. That's going to be log base 2 of n plus log base 2 of n minus 1 plus log base 2 of n minus 2 plus log base 2 of 1. We actually did a very similar computation to this before when we were trying to compare a factorial to an exponential with any base. There we took the natural log because it was easier to work with. Here we have log base 2. It's not that much worse. It's a very similar process. So what we can see is this just the same as like an area of a bunch of rectangles. And we can construct a curve which actually the area under which is less than the area of the sum of the rectangles. So that would be the integral under log base 2 of x from x equals 1 to up to n. Okay? And so if we work through that, we find that the antiderivative of log base 2 of x is x log base 2 of x minus x over natural log of 2. We have to have this change of base thing here, plus c. But overall, very similar. With the natural log, it was just x natural log of x minus x. Here we have to have this change of base correction factor here. But we follow through a similar thing. We apply the fundamental theorem of calculus, and we end up with this expression, n natural log of 2n minus n over natural log of 2 plus 1 over natural log of 2. So that is a lower bound for the lower bound, right? This is the best we can do. So that's a lower bound on comparison-based sorting. We came up with the lower bound for that, which is this. And what we can see is this is big omega of n log n. So here we are with our n log n algorithms. We can't do any better than that for a comparison-based sort. Interesting. So, but actually now we've seen algorithms that achieve that. So merge sort achieves that in average, worst, and best case. Quicksort achieves that on the average case. So we're actually doing really well here. And so the question is, can you do better if you don't use comparisons? What would I do if I didn't compare elements in the array? So that's something that we'll dig into a little bit more on Friday. Okay.